Welcome to AI Paper Slop. So if you're watching the AI coding leaderboards right now, you probably think autonomous software engineers are, about to take over the industry.
Right, yeah. Because frontier models are hitting, 75% resolve rates?
Exactly. But today we're doing a deep dive into a paper called SWE-Bench ProMax, Benchmarking Agents on Large-Scale Multilingual Code Refactoring. It's by Yuling Shi and a collaborative team from Shanghai Jiaotong University, Peking University, ByteDance, and a few others.
And this paper, honestly, it proves that the entire narrative of AI dominating software engineering is, it's a mirage.
Totally, because existing benchmarks mostly test these isolated single-file bug fixes. And even worse, an audit showed that nearly 60% of their unsolved instances contain flawed, overly narrow, or just overly broad tests.
Yeah, the grading rubric itself is basically broken.
Right. So SWE-Bench ProMax fixes this illusion by throwing agents into massive real-world refactoring tasks. We're talking coordinated changes across dozens of files in 7 different programming languages.
Which is brutal for them. Under these genuinely realistic conditions, the best model on the market, GPT 5.2, completely craters. It achieves only a 41.2% resolve rate.
And the kicker here, for you listening, is that open-weight models like GLM-5 and Qwen 3.5 are punching way above their weight class. They're nearly matching proprietary giants at a fraction of the API cost.
Which just proves that throwing more compute and, more money at a long-horizon coding task often just results in agents getting stuck in these expensive, unproductive exploration loops.
Yeah, we have desperately needed this kind of reality check. The whole industry has been operating under the assumption that the problem of autonomous software engineering was practically solved.
Oh, absolutely. But the data in this paper reveals we were essentially grading the AI on a massive curve, giving it tests that were simplistic and, frankly, completely broken.
Right. And because they were grading on a curve, the researchers had to break the rubric entirely. But before we get into how they built ProMax, let's talk about why the previous gold standard, SWE-Bench Verified, was failing so badly.
Yeah, the audit they point to is, it's damning.
What did they find?
Well, it revealed that nearly 60% of the unsolved instances had fundamental test defects. Specifically, about 35.5% had overly narrow tests.
Wait, overly narrow, what does that actually look like in practice?
So if you've ever written test suites, you know this pain. An overly narrow test might demand a very specific error message string, or assert that a dictionary's keys are returned in an exact specific order.
Even though the order doesn't actually matter for the function.
Exactly. The AI would generate a functionally perfect solution, but the test would fail it because it didn't match the arbitrary implementation details the original human developer used.
Oh, wow. So the agents weren't necessarily failing to write good code. They were just failing because the grading rubric was overly pedantic.
Right. And on the flip side, another 18.8% had overly broad tests, meaning they were checking for behaviors that the issue description never even asked the AI to implement in the first place.
That is a massive signal-to-noise problem.
It is. And the fallout was severe enough that OpenAI actually deprecated SWE-Bench Verified.
Really? I didn't realize they deprecated it.
Yeah. And beyond the broken tests, there's also an immense risk of data contamination. These models are trained on the internet, right?
Right.
So they've almost certainly seen all these public GitHub issues, the discussions, and the merged pull requests during their pre-training phase.
Okay, but if you manage a production code base, the detail that should terrify you about SWE-Bench Verified isn't just the broken tests, it's the scale.
Oh, the single file issue.
Yeah. 86% of instances in that benchmark only require modifying a single file.
Which is wild.
It's like designing a driving test, where you only have to prove you can parallel park one specific type of car in a completely empty parking lot. And then, because the AI successfully parks the car, we're declaring it ready to drive a delivery truck through Manhattan traffic at rush hour.
That's a great way to put it, because single file fixes are essentially measuring isolated code generation. If you tell an AI to find a null pointer exception in one file and fix it, that's just simple pattern matching.
Right.
True software engineering is about architecture, navigating massive code bases, understanding deep dependency graphs, and predicting the cascading effects of a single structural change.
Which means we need a task that forces the AI out of its isolated sandbox. We need a benchmark focused on refactoring.
Yes, refactoring is the ultimate test here.
So how do they actually define refactoring in the context of SWE-Bench ProMax?
In this context, it's the disciplined process of restructuring existing code without changing its external behavior. When you're managing technical debt or migrating legacy systems, it requires deep cross-file reasoning.
Because the behavioral invariance, the core logic of what the software actually outputs, they remain perfectly intact, right?
Exactly. While the agent tears down and rebuilds the architectural walls around it, if you break the API contract, the whole system comes down.
So the researchers went to incredible length to build a data set for this. They pulled instances from real GitHub commits, and they specifically restricted it to commits made after January 2025.
Which is a crucial detail for you if you care about evaluation integrity. It drastically reduces that training data contamination risk we mentioned.
Totally. And the dataset covers 7 languages: Python, Java, TypeScript, Go, C, C++, Maze, and Rust. But I have to push back on their methodology here for a second.
Okay, what's the issue?
They ran this rigorous 3-stage curation pipeline. They started with an initial pool of almost 30,000 candidate commits.
Right.
And they filtered that massive pool down to just 170 instances, from 30,000 down to 170. Isn't that an incredibly small sample size for a modern AI benchmark?
I mean, it sounds small, yeah.
Like, how can we trust the statistical significance of a data set that small when we're used to seeing benchmarks with tens of thousands of questions?
It's a super common reaction to question the volume. But in modern AI benchmarking, evaluation quality trumps pure scale every single time.
Really, even at 170?
Absolutely. Having 10,000 automatically scraped flawed tests gives you a massive amount of noise, not a reliable signal. What they did in their stage 3 curation is unprecedented in its rigor.
What they actually do?
Well, they didn't just scrape repositories. Human experts, heavily assisted by LLMs, manually reviewed everything. They took the raw GitHub issue descriptions and rewrote them from scratch to provide absolutely unambiguous specifications.
Because raw commit messages are usually terrible.
Exactly. A developer will write refactor off module and push the code. That means nothing to an AI agent that lacks the tribal knowledge of your engineering team.
Right. The human developer knows what the off module does because they talked about it in Slack for 3 days. The AI doesn't have that context.
So the researchers turned those vague messages into precise, mathematically self-contained specifications, and they manually purged all those overly broad or narrow tests.
Okay, so the remaining 170 are rock solid.
Beyond solid, they aren't just static text files of code. They are 170 perfectly curated, execution-based Docker environments.
Explain how that execution environment changes the evaluation, because that seems like a massive leap from standard code generation tests.
Huge leap. Instead of using static analysis to see if the AI generated the right syntax, they spin up a full virtual operating system inside a Docker container.
Okay.
The agent has to actually modify the code, compile it using native build tools, whether that's Cargo for Rust or Maven for Java, and then execute the test suite in real time.
So it guarantees that if the agent passes, it truly solved the problem in a live runtime environment?
Exactly. You're trading raw volume for absolute undeniable precision.
Wow. Okay, so now that we understand how bulletproof these instances are, we need to look at what actually makes them so brutally difficult. The paper dives into the scale of these ProMax instances, and the raw numbers are intimidating.
Yeah, the averages alone show why models struggle. The average gold patch, which is the optimal solution written by the original human developer, modifies 11.4 source files and 261.6 lines of code. That translates to over 8,100 tokens of modification per task. And when you factor in the test patches, it brings the total footprint to 15.9 files per instance.
Which is a completely different universe of complexity compared to the 86% of single-file tasks in SWE-Bench verified.
Completely different.
To make this concrete for you, let's examine a couple of the representative examples the paper highlights. They pulled an instance from NASA's F-Prime Flight software framework.
Oh, this one is wild.
It's a massive C++ project. The issue required the agent to unify a monolithic header file across the entire framework. To succeed, it had to touch 244 files.
244 files.
And change over 1,000 lines of code. It had to migrate aliases, configurations, and fixed with types across autocoders, hardware drivers, and operating system layers, all while keeping the compiled runtime behavior identical.
I mean, if you've ever worked with a large C++ code base, you know the linker is completely unforgiving.
Totally.
If the AI misses a single header inclusion in, like file number 243 out of 244, the entire build chain fails. The agent have to understand how types map across different namespaces and maintain that perfectly over hundreds of edits.
And then there's the plant UML task in Java. The goal was to modify the Gantt diagram engine to support hour-level resolution instead of day-level resolution.
That sounds simple on the surface.
Right, but it required altering 94 files and over 3,700 lines of code. It's the equivalent of doing open-heart surgery on a legacy codebase. Changing one fundamental variable type to the atomic unit of time from a day to an hour cascades through 90 other files.
Everything from the rendering logic to the serialization methods has to be updated.
Exactly.
And this perfectly illustrates why 99.4% of the tasks in this benchmark require what the authors call cross-file reasoning, and 98.8% require deep API semantics understanding.
Because the model has to build a mental map of the whole architecture.
Yeah, it has to apply a structural change to file A, realize that doing so alters the function signature for file B, navigate to file B, fix it, realize file B's new return type breaks a downstream test in file C.
And trace that dependency chain all the way to the bottom.
It's testing sustained context management. It's not just logic generation, it's architectural persistence.
So we have the ultimate gauntlet for autonomous software engineers. How did the absolute state-of-the-art models actually perform? They tested heavyweight proprietary models, Google's Gemini 3 Pro, Anthropic's Claude Sonnet 4.6, and OpenAI's GPT 5.2.
Right.
And they pitted them against the top open-weight models like Zipu.ai's GLM5, Moonshot's Kimi K2.5, and Alibaba's Qwen 3.5.
And the results are incredibly sobering. GPT 5.2 is currently the best model on the market for this, but it only hits a 41.2% resolve rate.
And that's using the OpenHand scaffold, right?
Yes. Claude Sonnet 4.6 hits 38.8%. So the absolute frontier of AI software engineering, powered by billions of dollars in compute, is failing roughly 6 times out of 10 on these realistic refactoring tasks.
We should probably clarify what we mean by the OpenHand scaffold, because the environment the model operates in plays a massive role here.
Yeah, so a scaffold is the software wrapper around the raw LLM. If you just ask an LLM to rewrite a code base, it'll just spit out raw text.
Right.
The OpenHand scaffold acts like a virtual workspace. It gives the AI access to a bash terminal, file editing tools, language server protocols to check for syntax errors, and the ability to run scripts and view the output.
It's the difference between asking an AI to write code on a whiteboard versus giving it a real laptop and letting it iteratively run the code.
Exactly. And OpenHand significantly outperformed a simpler scaffold called SWE-Agent, which mostly just provides basic search and replace text tools.
But even with a full virtual laptop, GPT 5.2 caps out at 41%. And the most shocking part to me isn't just the performance ceiling, it's the brutal economics behind it.
Oh, the cost breakdown is fascinating.
Claude Sonnet 4.6 costs an average of $4.77 per instance in API fees just to achieve that 38.8% resolve rate. Meanwhile, the open-weight model, GLM5, achieves a 36.5% resolve rate, which is statistically almost identical performance at a mere 24 cents per instance.
That is a 20 times price difference for the exact same result.
20 times. And Kimi K2.5 hits 32.9% for 72 cents.
It completely dismantles the assumption that proprietary, hyper-expensive models are infinitely better at complex, long-horizon reasoning.
If you look at that $4.77, it forces an obvious question. If I am paying nearly $5 for an AI to modify some files and it fails, where did the compute go? What is Claude actually doing with all those tokens and API calls?
So the researchers analyzed the agent behavior logs and identified a phenomenon they call unproductive exploration.
Unproductive exploration?
Yeah. Models are typically given a large step budget, sometimes up to 300 sequential actions allowed per instance. What happens is the agents get trapped in repetitive edit-revert loops.
Edit-revert loops.
They use their file editing tool to make a change. They run the test suite in the bash terminal, and the test breaks. Instead of taking a step back to understand the architectural flaw, they revert the file and then try the exact same failing strategy again.
Or maybe a minor mathematically equivalent variation of it.
Right.
They're acting like a developer who just keeps hitting compile, hoping the compiler will magically change its mind.
Precisely. They burn through their step budget, making expensive API calls and processing thousands of tokens of context history on every turn, without ever expanding the scope of their modifications to the peripheral files that actually contain the root cause of the error.
That makes so much sense.
Qwen 3.5 is a prime example of this failure mode. It took the most steps on average, over 140 steps per instance, but all that extra exploration didn't translate to a higher resolve rate.
So under the simpler mini SWE-Agent scaffold, all that wandering around just left it with the lowest score and a massive token bill.
Exactly. Even with great tools, if the model loses its architectural map, it just burns money in a loop.
Let's dig deeper into the anatomy of that failure. To truly understand why these state-of-the-art models hit a hard ceiling at 41%, we need to understand the mechanical breakdown inside the LLM when it attempts, like a 20-file refactor. Why exactly do things fall apart?
Well, the paper includes a brilliant trajectory analysis on Claude Sonnet 4.6 and Kimi-K 2.5. They mapped out exactly when the agents give up.
And what did they find?
They found a highly consistent failure mode dubbed incomplete refactoring. If you give these agents a task that requires changing 5 files or fewer, they track almost perfectly with the human gold patch. They find the exact files, make the correct edits, and pass the tests.
Okay, so they can handle the small stuff.
Right. But once a task scales past 10 files, the agents consistently tap out. The actual solution might require modifying 25 files, but the agent stops at 10 or 12 and declares the task finished.
Wait, so they aren't failing because they don't know where to begin. If they do the first 10 files correctly, they understand the core premise of the issue.
That is the insidious part of this failure mode. They find the core files instantly. If you tell them to change the time resolution in that Java Gantt engine, they will easily locate the central scheduling class and update the core data types.
But they fail to propagate those changes outward?
Exactly. They miss the peripheral call sites, the documentation files, the external configuration scripts, or the downstream dependencies. They do the heavy lifting on the main logic and then just put their tools down, leaving the overall system in a broken, inconsistent state.
The mechanism behind this is fascinating. As the agent fills up its context window with the text of those first 10 modified files, the attention mechanism inside the transformer model starts to degrade.
Yeah, it gets overwhelmed.
The initial architectural constraint, the core instruction of what it's trying to achieve, gets diluted by the sheer noise of 2,000 lines of new code. It stops paying attention to the global invariant and starts hyper-focusing on local syntax errors, which is why it forgets to update the peripheral files.
It loses the forest for the trees.
It's like hiring a sloppy home contractor. They successfully knock down a load-bearing wall to create that beautiful open-concept living room you asked for, but they completely forget to reroute the electrical wiring and the plumbing that was hidden inside that wall.
That's a perfect analogy.
You walk in, the living room looks spacious, but the house is functionally broken. The lights don't work, and there is water leaking through the floorboards.
And in a code base, leaving the plumbing broken means that 41% of the time, the agent accidentally introduces a completely new bug while trying to build your open concept living room.
Wow.
This ties into a fundamental empirical reality of software engineering. Refactoring is never just refactoring. It almost always exposes latent bugs. The paper explicitly notes that 41.2% of the refactoring instances in this benchmark also involved fixing a bug that surfaced during the restructure.
And what about new features?
Yeah, 43.5% involved adding a new feature simultaneously to support the refactor. Real code-based evolution is messy and compound.
Because when you rip up the floorboards, you realize the joists were rotting to begin with, and you have to fix those before you can lay the new floor.
Exactly. Agents fail because they lack the holistic architectural vision required to stabilize a whole system after a localized change.
They don't have the persistence.
Right. They don't possess the persistence to track a type mismatch error through 6 different abstraction layers of a REST application. They fix the immediate local error, hit another error in the next layer down, their context window gets overloaded, and they eventually just get caught in that unproductive edit revert loop.
Burning tokens until the scaffold times them out.
Exactly.
So what does this actually mean for you if you are an ML engineer or a technical lead building and deploying these AI systems?
Right.
We started by breaking the illusion of benchmark saturation. We looked at the brutal reality of multi-file execution-based refactoring across 7 languages.
Right.
And we unpacked the mechanical breakdown of why agents fail when the scope expands past 10 files and their attention mechanisms degrade.
The immediate takeaway is that you have to recalibrate your expectations of what frontier models can do right now. As long as models struggle with holistic, multi-file execution and stabilization, they remain incredibly advanced, highly capable code generators.
They're a great tool to have in your IDE.
Absolutely. But they are absolutely not autonomous software engineers. You cannot just hand them a repository issue, give them API keys, and go to lunch.
No, definitely not.
That 41% ceiling is a real structural bottleneck in how current transformer architectures handle sustained context and cross-file reasoning over long time horizons.
Which brings me to a final provocative thought to leave you with. We saw the data proving that open-weight models like GLM-5 and Qwen 3.5 are hitting near frontier performance on these massive, complex refactoring tasks at 20 times less cost than the proprietary giants.
Yeah, the cost difference is staggering.
Given that economic realities, shouldn't engineering teams stop burning cash on expensive proprietary API calls for large-scale code-based maintenance?
A great question.
If the performance ceiling is currently structurally stuck around 41%, regardless of who you pay, maybe the future of autonomous engineering isn't throwing money at a bloated API. Maybe the focus should shift entirely to building better, highly customized local agent scaffolds.
Environments like OpenHands that are fine-tuned to your specific code base.
Exactly. Powered by these cheap open-weight models, to push past this 41% ceiling on your own hardware, it completely reframes the economics of AI development. If you don't need to rent $1 million autonomous supercomputer just to get stuck in an edit-revert loop, maybe you just need a cheap local engine hooked up to a navigation system that actually remembers to reroute the plumbing when it knocks down a wall.